Hi everybody, this is tonight's homework, which is on exponential functions. Exponential functions. Prior in this course you've done several different functions, quadratic functions most recently in the last two chapters, linear functions, and absolute value functions. It's important to take a moment just to review these functions that you've done before in preparation for your final exam and also for framing the understanding of exponential functions. As a quick check, could you right now pause this recording in a moment and write an example of the graph view of an exponential function, a linear function, and an absolute value function. So pause and see if you could go ahead and do that. Hopefully, with a little thought, you were able to realize that the quadratic graph should be a parabola, either opening down or opening upwards, that the y equals mx plus b would have to have a constant slope. It could have a slope of 0, an undefined slope, a positive slope, or a negative slope. And the absolute value function, if you remember way back in the beginning, that's where you're going to have a V shape. It's a linear equation sort of glued together at a V point. It was simply, if it was y equals the absolute value of x, the lowest point it could get is 0, because that's the lowest absolute value of x, and right straight up. So these are some of the possible examples you would give. Needless to say, when it comes time to the final exam, you need to know all the relationships here that involve the intercepts. Where will that appear in the equation? What's the vertex? What's the axis of symmetry? You need to know the slope. As we said, the y-intercept. You need to know how to express a vertical line and a horizontal line. An absolute value, how to find that low point on the absolute value. It's also important to note that the slope is constant on these linear equations. The slope is ever changing in a parabola. The slope on an absolute value equation is going to be constant until you get to the vertex, and then it's going to be the opposite slope after the vertex. So now when we get to exponential functions, there's something that's different. In the quadratic functions, x, the variable, was squared, and then it was added on as well. And in linear functions, the variable was constantly multiplied by a rate of change, for example, 3/5. In an exponential function, the variable counts the number of times by which you are multiplying by the same factor. So in an exponential function, x is the variable, and the number that is being multiplied is the constant. The rate of change, however, will not be constant, because as things grow by, say, 20%, the amount that they increase each time is different. Therefore, the slope between any two x values will be different. Could be that it's getting higher, could be that it's always getting lower. We will explore that more in the future. The point on that is that there is no constant slope. X for us will be integer values. We will not be dealing with fractional exponents in this class. A significant part of the analysis of these exponential functions will be whether or not this value, the thing that is constantly multiplied, is between 0 and 1, or simply greater than 1. For our first example, we're going to talk about if you had a photo of a super small grain of sand, 3 millimeters on a side. That's how small the grain of sand is. And you blew it up, and you enlarged it by 50%. To do this equation, you don't really want to multiply by 0.5 and then add it on. You want to multiply it by 1.5 because you get the whole 3 millimeters plus 50% more. So 3 times 1.5 is going to give you 4.5 after one enlargement. Now, you're constantly multiplying by 1.5, and you will do it x times. So every time you get a new answer, the following time it will be 1.5 times larger, meaning the rate at which it increases is not constant, and it's constantly going up more and more every single time. So if you could kindly fill out the table xy, and let's do it for 10 iterations, so 10 examples where you say 3, you put in 3, you're starting with 3, times 1.5 to the 0, anything to the 0 is 1, so the first example would be 3. The second one would be simply 3 times 1.5, that would be 4.5. So fill out the next 8 values and then plot them on a graph showing the change over time for each variable value of x. So this is the first value. X is 1, x is 2, x is 3. Go ahead. Hit pause. Okay, so if you were successful with that, here's roughly what your page should look like. These are the calculations that were done for the first 4 iterations of x. Each one is constantly multiplied by 1.5 an additional time. As the power goes up from 3 to 4, it's an additional 50% greater. Your table, your XY table, should look something like this, where you're starting at 3. As you rise, the final value, 173, is quite large, and of course every single time after that it would be 50% larger still. That is sometimes hard to see in table view, but if you see it graphically, you can notice each time it's going up 50% more, so the amount that it changes is so much greater because the starting point is 50% larger, then the next starting point is 50% larger, so each increase is on 50% more than the prior. So the constant rate of 1.5 produces an ever-growing change per increase in x. It's important to note at this time that working backwards with powers from 1.5 to the 4th to 1.5 to the 3rd is essentially the same thing as division, dividing by 1.5. This has a relationship to reciprocals. Dividing by 1.5, also known as 3/2, is the same thing as multiplying by 2/3. As you go back in time, this does not approach 0. It's super important to realize that. As you went back in time, for example, if this image of the 3 millimeter grain of sand had been 50% smaller, back in time it would have been 2/3 of that 3. In other words, it would have been at 2. You can check that by doing 3 times 10 to the negative 1. Times 1.5 to the negative 1. So 1.5 to the negative 1 is the same thing as multiplying by 2/3. You're divided by 1.5. This will approach 0. It will never get to 0. That's a super important point. As you divide something, there's always a piece left. You keep dividing, there's always something left. You are approaching 0 as you go back in the past, but you will not get to 0 because you always had something that was increasing by 1.5. Similarly, this never reaches vertical. It's always 1.5 times it. It's always 50% greater. If you get to 1,000,000, it will be 1,500,000. If you get to 1 billion, after that it's going to be 1.5 billion. Okay, for tonight's homework, you're going to graph and create tables for 2 exponential functions. These functions are related in some ways, and they are entirely different in others. You need to pay very close attention to the different values you get in your tables. You will create 2 tables, one for the first function, one for the second function. Each one of the tables will have values from -6 all the way to 6. So including 0, that will be 13 different calculations that you will do to get the y output for each x input. You will do that for the first equation. You'll make another table. You'll do it for the second equation. Then you will graph them. It's perfectly fine if you'd like to graph them both on the same xy axis. Make sure that you have enough room. For example, you should make sure that you check to see that 1.3 to the 6 times 20 is going to fit on your y-axis. So that's your entire homework. Just do that very carefully. Take a moment to notice any relationship that you can see or anything that's almost a relationship between, for example, an input of -5 in one function and 5 on the other function. Are they the same? Are they different? And why? This is a very important point. So show your work carefully and then do the analysis, and we'll talk about it in class. Thank you and good luck.